Good day, and welcome to our webinar on increasing critical crude oil pipeline reliability by means of an innovative retrofit sealing solution. Today's program is brought to you by CFE Media and Technology and is sponsored by John Crane. Today, from John Crane, we'll be joined by Raul Escontrias, North America Pipeline Account Manager, Brian Calfrin, Regional Engineer, Jim Wasser, Global Director of Design Engineering, and John Morton, Senior Product Marketing Manager. I'm Kevin Parker, Editor of Oil and Gas Engineering and other publications from CFE Media and Technology. Crude oil pipeline pumps traditionally suffer from seal leakage due to the fretting or wearing of the dynamic O-ring, rather than wear to the dynamic seal faces. Surveys and root cause analyses performed on equipment demonstrate that solids and debris contained in the pumped product cause secondary seal damage and ultimately seal failure. Moreover, pumping stations that serve transmission and gathering pipelines are often remote and unmanned. Use of a reliable secondary seal increases both pump and pipeline reliability. A more robust, non-dynamic secondary seal has been developed to eliminate these kinds of damages and failures. It cannot hang up nor wear the shaft or secondary sleeve. In addition, reduced sleeve fretting maintains seal integrity, delivering improved spill prevention, and is valuable to operators in terms both of assets protected as well as critical asset expansion. Stay tuned for today's presentation and discussion. You'll learn to identify the common causes of mechanical seal and subsequent pump failure in crude oil pipelines, quantify the immediate and long-term costs and implications of seal failure, and understand a solution that solves common pipeline seal failures and extends mean time between replacement. To get the best results from the webcast platform, please make note of the following as you participate in today's event. If you are having technical problems, click on the question mark at the top right-hand corner of your screen to bring up a list of system checks to make before escalating to an online technician. If you are experiencing issues with the slides or audio, please refresh the browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume settings of this webcast by adjusting the volume on your computer or by adjusting the volume on the platform. If you do need a technician, type a message into the Ask a Question box and someone will get to you as quickly as possible. Answers to technical questions will appear in the Answered Questions box on the left-hand side of your screen. The Ask a Question box is also used to ask the speakers questions. You may ask questions at any time during the presentation. We'll get to as many as time allows. To download the presentation slides and certificate of completion, use the Event Resources box on the left-hand side of the screen. You can download the presentation and certificate of completion until the conclusion of the webcast. The link will break when the webcast signs off. This webcast is being recorded, including the Q&A session. We'll send you an email message within a week with a direct link to the webcast archive. I'd now like to introduce today's speakers. John L. Morton is a Senior Product Marketing Manager for John Crane, based in Slough, Berkshire, United Kingdom. He is also Chairman of the European Sealing Association. Over the last 36 years, John has held posts within the John Crane Global Organization, beginning in engineering and product development before taking on sales responsibility and moving into a marketing role. He has been involved in the design of or has product managed many John Crane products over the last 20-plus years. John represented the sealing industry at the World Trade Organization and has participated in a European Union trade delegation. John obtained his MBA from the University of Reading in 1998. Jim Wasser joined John Crane in the Chicago office in 1986 and has held a variety of positions within the engineering department. He is currently the Global Director of Design Engineering, responsible for wet seal development, material maintenance, and the global test labs. He holds a Bachelor of Science in Mechanical Engineering from Illinois State University. Brian Calfrin is a regional engineer with John Crane in Pasadena, Texas, with more than 17 years of experience with mechanical seals and related systems. His duties include design engineering oversight, analysis, and recommendation formulation, along with design evaluation of existing and proposed mechanical seals using finite element analysis software. Brian is also responsible for training both customers and John Crane personnel in mechanical seal application and troubleshooting. Brian is a member of the Texas A&M International Pump User Symposium Advisory Committee and holds a Bachelor of Science in Mechanical Engineering from Drexel University. Raul S. Contreras is the North American Pipeline Account Manager for John Crane, based out of Houston. He joined John Crane in 1997 and in his current role serves as a technical resource specific to the pipeline industry. His primary duties are interfacing with corporate engineering groups for pipeline operators to establish best practices for design criteria, assist with on-site troubleshooting, formulate recommendations on new applications, and facilitate client training. Raul has held additional engineering roles within John Crane, including reliability and regional engineering positions in the United States in the refining, specialty chemical processing, and petrochemical markets. As a graduate of Texas A&M University with a Bachelor of Science degree in engineering, Raul has over 21 years of technical field experience. Raul, welcome to today's webinar, and please go ahead.
Thank you, Kevin, for the introduction and the brief summary on today's webinar topic. On behalf of all of the John Crane representatives, it's a privilege today to have the opportunity to present the technical session related to the midstream and pipeline industry. We're going to go ahead and begin with a review of application considerations associated with pipeline. Typical to any other application, in evaluating the most reliable mechanical seal and support system arrangement for a given application, it's always going to be imperative that certain process and equipment information be identified on the front end. So whether the initiative entails a large-scale capital project in the form of a new pipeline build, 10 pumping stations, 20, 30 pumps, or even a simple pumping station retrofit opportunity, the criteria under the pipeline application considerations all going to be considered critical to ensuring a reliable solution is offered. So generally, this information will come from the equipment operator direct or perhaps through an EPC. In some cases, it may even come from the pump OEM or a remanufactured shop, but the seal suppliers typically going to just want to ensure that as much of this data is presented on the front end to ensure due diligence in the review from an application perspective on their respective end. So as you can see here, you've got various fluid properties such as specific gravity, vapor pressure, viscosity. All they're going to be critical in terms of understanding how the fluid in the pump behaves during dynamic operation. And this is going to impact how we calculate seal flush rates. It's going to be critical information to determine estimated leakage rates across the application. So the fluid makeup's also critical. It's always going to be critical. We also need to understand the potential for solids, the potential for chemical exposure. Does the process stream have any sort of amine or H2S concentration that might force the supplier to move and use one material versus another? So these are all considerations that need to be clearly identified on the front end. In terms of evaluating the seal performance through means of finite element analysis, the operating pressures, operating temperatures, and speeds, especially in the pipeline business, given that these critical variables are changing, that range conditions are going to be critical in terms of predicting both thermal and pressure distortion at the primary sealing rings, the primary sealing interface. So once again, we ask that this data clearly be defined on the front end, and then obviously understanding the overall hydraulic build of the pump. Whether we're dealing with a BB1 style pump, a multi-stage BB3 machine, or even a vertical turbine booster pump, a VF6 style machine is going to be critical to understanding the seal chamber pressure, and how the mechanical seal, what types of pressure ranges the mechanical seal is being exposed to. So how does pipeline differ from, let's say, a downstream application in terms of refineries, petrochemical plants, maybe even a specialty chemical plant, where the application tends to be a little bit more firm in place. They're typically supported with spared equipment. When you look at the challenges associated with pipeline, you're going to typically see a range of batch fluids. This can be varying API crude oils in a single pipeline, or even in some cases, and what's becoming more the norm, is to pump crude oil one day and then move to a more refined product such as a butane or maybe a nat gas, perhaps even a diesel style liquid that's going to have significantly different properties from crude oil. And so that's always a challenge that we face. Obviously, having pumps operating in series where the equipment operator would like to utilize one seal design across the entire range, and having stepped operating pressures of 300 to 400 pounds per pump, high viscosity startups, high pressure rating requirements, all of these become contributing factors that differ somewhat from a typical operating plant in terms of a refinery or petrochemical environment. I think one of the more significant differences is the fact that these stations tend to be unmanned, they're remote, and so they're operating without unlimited site utilities. The majority of the downstream business will have cooling water, steam, nitrogen, all utilities that are available as supplemental additives to the process or to the equipment itself that help improve reliability. And so the pipeline business operates in a somewhat less ideal environment when you take these typical design challenges under consideration. Probably one of the more significant differences is the high pressure rating requirement of operating a pipeline. And attempts to minimize seal design configurations that can impact spare seal inventory or potentially complicate the maintenance work for field technicians, most operators prefer to apply the same design concept across a range of operating pressures, that being across the pumping station, which can be fitted with 2 pumps to as many as 5 pumps, in some cases as high as 6 is what we've seen in the industry. Now, these pumps typically are going to have an identical pump footprint, and the operator end user tends to want to utilize the same seal design concept across those pressure portfolios. So sealing high pressures is always going to be a challenge due to the associated thermal loads that deviate from one pump to the next. And then you have the requirement of mitigating phase distortion associated with these pressure variables. The focus is always going to need to be placed and evaluated on material selection, face geometry, utilizing lower balance ratios across the design, and all those variations can go through an evaluation and detailed through an FEA finite element analysis process. Now, depending on the fluid media and your seal face material combination, your reliability and leakage rates can certainly vary at lower pressures when you design for such a high static pressure rating. And so that's the one thing that we definitely have to be mindful of, is that we know that mechanical seals designed for a true operating condition in the seal chamber will always exhibit an improved performance and a more predictable have a more predictable leakage rate, as opposed to the design that's designed for a much higher pressure when compared to normal duty. Here we're looking at the pressure limits for mechanical seals as defined by API 682. I won't go into the definition of each, but what you're seeing is a typical static pressure limit, a dynamic pressure limit, and then a maximum allowable working pressure limit that are clearly defined within 682, 4th edition. Now, I think it's critical and important to understand that API 682 mechanical sealing standard is primarily used in the petroleum and chemical industries, but it's not uncommon for midstream or pipeline operators to request that seal assemblies are designed to the intent of 682. So even though the design limits in terms of your operating pressures and equipment shafts, I believe the upper pressure limit currently for 4th edition is 615 pounds, and a shaft diameter of 4 inches as the upper limits, pipeline companies and midstream operators are still targeting a build to the intent of criteria. even though we have experience with equipment and operating pressure significantly higher than both of those defined within the range of 682. So when you're looking at regards to pressure limits and definitions, this often results in some varying interpretations as to which components within the seal assembly actually have to meet pipeline MAWP criteria. We spoke briefly earlier on how designing for higher pressure ratings can impact leakage rates and then translate the varying performance across that respective operating range. So the dialogue needs to be had between end user operator and the seal supplier to ensure that the design criteria, which can influence the sleeve component, the gland component, the drive mechanism component that has to accommodate for associated thrust loads to keep the rotary assembly locked in place, all that needs to be considered. It should also be noted, however, that API 682 does define the pressure casing to include the seal chamber, but excluding of the rotating and stationary sealing components of the seal assembly. So these are the components that are most critical to controlling and mitigating primary seal leakage, and that's where the dialogue between the end user and the seal supplier needs to be executed to ensure that both parties understand how the seal is meant to be designed relative to the various operating pressures by definition. I'm going to transition here to Brian Calfrin, who is going to go over crude oil application specifically, some of the material considerations. Brian, if you could please proceed.
Thanks, Raul. So, to focus a little bit further on the material aspects and specifically materials for pipeline seals and crude oil applications, we look a little bit and talk about faces and secondary element materials of construction, and common and more across most mechanical seals and specifically in crude and pipeline applications. There's pros and cons to each. Carbon graphite on the left-hand side of your screen is a very common face material, and typically it's going to be a carbon graphite that's impregnated with some kind of metal, be it an antimony or a nickel. The advantage of using any type of metal-filled carbon graphite primary ring is it offers you very good performance in terms of the lowest leakage and very good overall natural lubricity of that material. When we start talking about higher pressure applications in pipelines and specifically in crude oil where there's potential for abrasive or viscous, high viscosity excursions, the relatively soft nature and makeup of carbon graphite presents some limitations. So in practice, when we look at abrasive service, particularly in crude oil, typically we're looking at two hard face materials to kind of overcome some of those limitations. When we start talking about hard faces, we're focusing more on silicon carbide and tungsten carbide as our kind of main focus areas of materials of choice. Silicon carbide, typically they're either going to be reaction bonded or self-centered grades, and they're very designations based on the manufacturing process. Silicon carbide overall is very high strength, very good thermal shock resistance, and it maintains that broad material strength across a very high temperature range. These are advanced ceramic materials, so we typically, as seal suppliers and designers, will try to maximize pressure velocity characteristics and tribological properties by running dissimilar grades of one another, especially in high viscosity applications such as crude oil. Because of the very kind of robust nature of the material, it's recommended to use a more robust drive design for seal rings manufactured of these materials, and that helps to avoid potential hang-up that can occur, especially when these harder materials kind of contact comparatively softer metal components such as retainers and other adaptive hardware components in the seal. The limitation of silicon carbide is that it's prone to thermal shock, so in other words, heating up and rapid cooling that can actually result in failure or fracture. Tungsten carbide overcomes that. It's very resistant to mechanical and thermal shock. It's a very dense material, cemented carbide, typically using a nickel-bound agent in addition to the natural tungsten. The disadvantage of using tungsten carbide is that while it's very mechanically tough and resistant to thermal and mechanical shock, it's very susceptible to heat checking, which is a little bit of localized cracking of the subsurface of that material due to essentially expansion and contraction from rapid heating and cooling. So heat checking damage is kind of irreversible and typically results in much higher leakage once it does occur. If we look at a composite grade such as a silicon graphite composite material, just as the material definition implies, it's a makeup of two different seal face materials. And what it does is tends to marry and take advantage of the pros of the carbon graphite and the silicon carbide in terms of maximizing the lubricity and taking advantage of the carbon graphite natural lubricity, but then marrying that with the improved material strength of the silicon carbide, so it gets you beyond some of the pressure limitations and abrasive limitations that you may experience by just considering a carbon graphite grade on its own. Secondary sealing elements, which we're talking about, namely O-rings and gaskets, typically they get evaluated by compatibility with the process. When we talk about pipeline applications, and especially crude oil, we're looking at much higher pressures usually, so beyond 1440 psi or 100 bar, higher durometer O-rings may be used to prevent extrusion of softer materials through clearances and gaps within the seal. And we may look at even more specialized backup rings or thermoplastic designs or even alternative secondary elements altogether to overcome some of these challenges. Speaking about crude oil applications more specifically, when we're sealing crude oil, there's a number of different considerations that should be given to the fluid properties, and they're typically identified by the end user or the procurer of the equipment. But primarily we're concerned as seal suppliers with the specific gravity and viscosity values, especially at relative temperatures. Crude oil will generally have 4 levels of classification. It'll be referred to as light, medium, heavy, or extra heavy crude. And those classifications are established by taking that breakdown and varying chemical composition of the crude oil and establishing a functional API gravity classification, where you establishing the relationship between the specific gravity and the API gravity using the calculation that you see on the screen in front of you. So by this definition, crude oil classification would be a light crude having an API gravity higher than a 31, medium crude oil being in the API gravity range between 22 and 31, heavy crude between 10 and 21 API gravity, and then a very extra heavy crude having an API gravity below 10. That provides some designation and some indication as to the viscosity and kind of the severity of the duty that the mechanical seal is going to be exposed to. So considering the crude oil and the chemical components that are typically associated with it, it can range from very low boiling point fluids all the way up to sulfur, wax content, asphaltenes, sand, pipeline rouge, just you name it, varying degrees of constituents in that process. And these are exposed particularly many challenges to mechanical seals in terms of long-term reliability and maximizing performance, particularly in the context of the components of the sulfurs, the waxes, and any sand or pipeline rouge in the line. They're very difficult to filter and separate these constituents out of the crude oil. Plan 31, your cyclone separators, as you will, are very ineffective actually in crude oil, depending, especially as the viscosity increases. So it's very hard to kind of clean up crude oil, if you will, to make a better environment for the mechanical seal. So what that means from a seal design perspective is that every component within the seal needs to be kind of robust enough to withstand the arduous duty of the application. When we throw in factors such as varying speed and pressure, varying viscosity, then a detailed consideration into the mechanical seal design in terms of space, balance, pressure, velocity, contact pressures, all these variables need to be evaluated, and oftentimes simulations are run to get the maximum in terms of performance with minimized leakage and longest seal life. And when we factor in several other things, such as these heavy constituents in these small restrictive areas of the seal, can now lead to maybe hang up and clogging of secondary elements and components such as that nature, then really a robust seal design capable of withstanding this broad range of varying processes is really key to long-term reliability in crude applications. Some of the typical seal arrangements that you will see in crude oil would be presented on the screen in front of you right now. In API 682 terminology, you're looking at an arrangement 1, arrangement 2, or arrangement 3 seal. We'll talk about arrangement 1 and arrangement 2 in the next few slides. I'll mention briefly that arrangement 3 seals, which would be your dual pressurized configurations, they're typically defined as a contacting wet face-to-face configuration that's shown on the screen, and we're usually deploying those in environments where the pump is subjected to varying ambient conditions, swinging to kind of sub-zero temperatures, and also multiple API gravity liquids. What happens is that variation in ambient temperature can impact the viscosity of the crude oil, especially when the equipment is not operational. So we have potential for freezing of processes, both within the flush, drain lines, high torque scenarios of the equipment that could result in excessive face damage or grain pullout and damage to drive locations within the seal. So the 3 contacting wet face-to-face arrangement allows for more improved isolation of those components, especially when you're talking about varying temperatures and startup conditions. So provides a little bit more of a stable interface in some extreme conditions. In terms of arrangement 1, which would be a single seal here, type A seal. So type A is again a nod to API 682, where a type A seal is essentially a low temperature O-ring secondary sealing element, multiple spring design here. And these are typically common in crude oil pipelines, single cartridge seal using this very common type A assembly following the intent of 682 4th edition. And it doesn't follow 4th edition to the letter because majority of the pressures are outside and sizes are outside of the scope of the standard. When we're looking at pumping crude oil and that equipment is subjected to a high percentage of solids and also shaft movement, typically the dynamic O-ring could be a weak link in the chain. It could be susceptible to fretting damage and degradation, and typically that's the component that will fail in a crude oil application. There won't be a lot of face damage or degradation of the seal face materials. It's usually that secondary sealing element that can degrade and cause the seal to fail prematurely. So especially in these higher pressure applications and with solids and shaft movement, an alternative engineered secondary sealing element can be implemented now to provide a non-pusher element in this location, and that eliminates some of the concerns with fretting and breakdown of those O-rings. Kind of the natural question would be, why could you not use a type B seal, which is a low temperature metal bellows design, which also has a kind of a static secondary sealing element? The disadvantage there is those seals will not be rated for pipeline pressures, and they will not be able to kind of withstand the variance in viscosity and the varying process application conditions that you're going to see because of the limitations of the hydraulic balance of the bellows design. So when you're looking at type A seals, it's better to approach it from the standpoint of how can we address the limitation of the type A seal in terms of improving the dynamic O-ring And that leads us into the slide you see in front of you now, which shows an arrangement 2 or a dual seal configuration. Instead of just a single bushing on the back end of the seals of containment, this actually is depicting a more positive end-face seal in terms of a full dry running contacting containment seal concept in terms of just a bushing with some clearance. The main difference here is that we're calling out the engineered secondary sealing element that addresses those concerns with the dynamic O-ring fretting and breakdown to abrasives and particulate that can be in the crude oil. Oftentimes we're asked about utilizing a dual unpressurized wetted seal, which would be utilizing a Plan 11 and an API Plan 52 buffer fluid. This is not recommended for crude oil, and the primary reason is there's oftentimes in these pipeline installations there's a lack of utilities, and due to the inherent dirty nature of the crude oil, the buffer fluid is a low pressure fluid between the two seals. Eventually the leakage of the crude oil past the inner seal, just due to normal operation over time, is going to lead to just poor containment seal reliability. It essentially becomes a preventative maintenance nightmare, and that buffer fluid in that reservoir will be just an emulsion of crude oil and whatever that oil started out as to begin with. So when you consider normal primary seal leakage, potential for loss of buffer fluid through leakage past the containment sealing interface, the maintenance test, which is going to be including frequent draining and replenishing of this buffer fluid, it just will be a nuisance to the pipeline operator. So I'll talk briefly about some of the common piping plans that you'll see in crude oil applications. So API Plan 11 is the most commonly used in pipeline industry, especially in crude oil as well. It's just a relocation or injection of the pump product from a location in a discharge pressure region, and that's injected into mechanical seal, and that provides lubrication and removes heat from the mechanical seal faces. So primary objective of Plan 11 is to just provide cooling and lubrication, and you may hear it referred to as a discharge bypass, but working closely, the pipeline operator and the seal supplier can determine the suitable flow rate that's required, and that suitable flow rate factors in a couple things, looking at the total heat load based on seal face frictional heat, viscous shear, any heat soak, and the amount of flow that's required to maintain a suitable temperature rise in that flush, so that we're not running into any issues with high heat, high coking, or things of that nature. Plan 11 is very easily maintained. It's typically flow is controlled via an orifice or a choke tube, or even in some cases could be some properly sized length of tubing for restriction. Disadvantage of Plan 11, essentially in crude oil and pipeline service, there is a potential for pipeline rouge, sand, and things of that nature to kind of plug orifices and lead to clogging. With crude oil, in terms of leakage and leak detection, we try to look at a couple different piping plans here. We'll talk about those briefly. 65A and B. 65A is utilized in Arrangement 1, single applications, provides leakage detection, and utilizes close clearance bushings to direct that leakage to the gland plate to a liquid reservoir through an orifice and through a drain recovery system. So through the normal operation, the leakage flow through the orifice is fine. As leakage increases, the orifice downstream restricts that flow, and then you get a level increase, and that can be tied to an associated level alarm, and controlled shutdown of the equipment can be executed at that point. Orifice sizing is very critical with a 65A. So typically in crude oil, we have to be cognizant of viscosity and contaminants and sizing internal diameters and orifices effectively to make this system work to its optimum. The difference between 65A and B is that the outlet from the liquid reservoir in the 65B has a valve instead of an orifice. So the difference here is that this valve can now give you a better indication of leakage over time. The disadvantage is that valves have to be kind of actuated manually as the level increases to dilute and drain that excessive leakage level. 66A is also used in arrangement applications and uses atmospheric, providing atmospheric detection to seal leakage. From a practical perspective, the idea is that you would get a pressure increase as more excessive levels of leakage moved into this cavity. From a practical perspective, it has several limitations based on determining a suitable alarm and shutdown set point based on the viscosity of the crude oil. In reality, relying on pressure with crude oil is not as accurate as it would be to monitor flow or accumulated leakage over time. And that would be more comprehensive in terms of monitoring seal health and condition. And now I'll transfer over to John to talk about more of the technology improvements we touched on briefly.
Thank you, Brian. Pusher seals, i.e. those seals whose secondary seal is a dynamic O-ring, have been used in sealing crude pipelines for many, many years. In clean and lubricating products or environments, O-rings are a well-proven sealing solution with millions of installations in all types of applications. The key is to operate in the dynamic nature of the secondary seal. It has to compensate for a lot of potential movement. That could be compensating for seal movement attributed to face wear, compensating for movement caused by changes in the pressure regime operating on the seal, or compensating for shaft movement caused by the hydraulic conditions found in various pumps. This movement of an O-ring can be either sliding or rolling, but as soon as you introduce a dirty or abrasive layer rather than a clean lubricating layer between the O-ring and the shaft or the sleeve, then the concept of fretting is introduced. It can happen in clean fluids, but it is far more pronounced in dirty fluids or products. This fretting and the subsequent build-up of dirty, clogging or waxy products around the O-ring can manifest itself in many ways. The obvious and most damaging ways for seal health are shown here. The constant movement of the O-ring, often small movements many times a second, can cause abrasive wear to the O-ring and the sleeve or shaft. This is shown in the lower images. This will result in severely degraded and impaired O-ring and a leakage path past that O-ring. If this is allowed to continue, hang-up of the primary seal will eventually occur, and excessive leakage and no further dynamic ability of the primary seal. This hang-up can be exacerbated by the build-up of clogging substances around other dynamic features, such as springs. In all instances, seal life will be severely compromised. Mechanical seal vendors have been aware of the difficulties of sealing crude oil for many years. As line pressures and line hydraulics have increased, then these issues have become more pronounced. Various steps have been taken to try and mitigate the resultant reduced seal life and leakage. These steps have included increasing the hardness of the seal interface materials. This helps where poor lubrication is experienced at the interface, but is often not the case, and the dynamic seal faces come out in excellent condition, yet the seal has suffered excessive leakage. Introducing a lubricating regime to the seal face. Again, this can have mixed effects. More lubrication at the seal face can improve the dynamic operation of the seal, but will not prevent hang-up. and will increase seal leakage. These lubricating features include hydropads, spiral grooves, or changes in dynamic balance. The use of filters to clean the liquid that is entering the stuffing box through the recirculation line, maybe an API plan 12 or 31, to promote clean lubrication of the seal faces and dynamic O-ring. Removing the traditional dynamic secondary seal with what is termed a non-pusher style seal, such as a rubber bellows or a metal bellows design. This removes the dynamic movement directly in relation to the shaft or the sleeve and will reduce potential for fretting. And finally, changing the seal arrangement and API lubrication from an API seal arrangement 1 to use dual seals and self-contained seal support systems, either as a pressurized arrangement 3 or an unpressurized arrangement 2, to ensure that the clean lubricating liquid in a controlled environment is at all times being circulated around both the secondary and primary seal to ensure optimum seal chamber conditions. I will now hand over to Jim to take some of the technical issues.
Okay, thanks, John. So after reviewing all of the information that was collected from our end users and looking at several different seal failures that were experienced on crude oil applications, we found that, as John mentioned, that the secondary sealing element was the main problem and the main cause of failure. So we looked at the differences between a pusher and non-pusher, and the left side of the slide is a pusher seal. So as the seal wears, the green and the yellow components are wearing over time, that O-ring must follow and track that primary ring. For a non-pusher design, it doesn't. That primary ring and mating ring track due to pressure that's exerted on it, the line pressure. And the secondary sealing element stays in place. It tracks the primary ring, but the drive mechanism stays in place, and there's no interaction between the metal and the elastomer ring. So another cause of failure that we saw was the shuttling. The shuttling led us to the secondary seal problem, the O-ring. The O-rings would start to fret, they would leak, they would hang up, and you would have a seal failure. The faces themselves, the sealing interfaces, were normally in very good condition. We used a hard face material, silicon carbide, what Brian mentioned, and we kept with that hard face material because it resisted wear and it resisted the abrasion. We saw no reason to go to a more advanced material or material interface, such as a diamond-coated face. The majority of the failures that we saw was on that secondary sealing element. So looking at this seal drawing, the blue, the L-shaped, that is what we are calling the non-pusher secondary sealing element. It's a 90 durometer O-ring, or 90 durometer elastomer. It's a hard elastomer material because it holds up to the abrasion that could be due to the solids in the fluid. But you can also, we have applications where we have applied it down to 70 durometer for different applications. As was mentioned earlier, it is easy to design a seal for a certain pressure. It is difficult to design a seal for pressures from 50 psi to 1500 psi. You design a seal for 1500 psi, it will leak a lot at 50 psi. So the trick was to come up with a seal that wasn't greatly impacted by the change in hydraulic pressure. When you look at this elastomer sealing element, if it was a full convolution bellows, which has been out for 60 years, that convolution bellows, full convolution bellows, will collapse under pressure. That collapse causes a change in the pressure percentage acting on the faces. In this case, there's no change in that face loading. The percent of face loading stays the same. The component itself will shuttle and move with the shaft. And we have seen applications as high as 10 or 15 thousandths of an inch, and we've actually designed it to handle 31 thousandths of an inch in each direction. So how is that done? If you look at this slide, you can see the loads, the forces that are acting on the elastomer ring. It's acting to push the ring forward to create that seal between the elastomer ring and the primary ring. It's also pushing down onto the drive, that stub sleeve, that is creating a drive. Now, when you do see a shuttling movement in the shaft, you start to see axial movement of that entire seal. If you look over to the right, you can see what happens to this elastomer sealing element. It will move back, but still stay in contact with that primary ring. And then that high-strength anti-extrusion ring, which is in the lower left of the blown-up screen, that will help keep that elastomer from extruding. But when it moves to the left, it moves along with the primary ring, tracking that, and putting that load on the face, keeping it a constant load on the face, but also providing the seal that's required during the shuttling. This concept was tested over 8 million shuttles, or 8 million cycles, and there was no damage to that elastomer ring. And now I'm turning it over to Raul.
Thanks, Jim. I appreciate that. We're going to conclude the session today just going over a couple of the field installations that we have. As you can see on your screen in front of you, we've got several different installations, various shaft sizes, 5.510-inch shaft, 140 millimeters, 3 pumps up to 1,200 pounds of pressure, varying speeds, installed in November of 2017. We've got another application, actually a dual unpressurized system, installed in February 2018 without incident since original installation. And we had another one, smaller shaft diameter, 3.1375-inch shaft, installed in March 2018, have been yet to been pulled, single seal concept, but turning at 3580 RPM. So when you look at the matrix that we now have presented before you, what you're seeing is a different assortment of sizes and temperatures and speeds, viscosities and specific gravities, that key API gravity indicator as to what grade of crude oil classification of crude oil we're dealing with. And what you've seen is is across the entire operating range, temperatures, pressure, speed, sizes, different configurations, single seals and dual seals. We're upwards of 150 units in the field actually functional, with approximately another 150 currently in manufacturing or have actually been released to the field, just not operational. So in terms of the historical background and the field verification, what we've seen is that the performance has pretty much agreed with what we saw within the testing in the controlled laboratory at our main headquarters. It's almost validated what we saw in the lab. So performance has been exceptional across these various operating conditions. And what we're going to do now is we are going to show a brief animated video that demonstrates some of the axial movement relative to the pump and how the seal behaves that Jim touched on. If we could please roll the animation.
Good. Well, thanks, Raul, and thanks for your expert presentations. Let's turn to our question and answer period. This question, I believe, is meant to be directed to you, Brian. Do you ever see API seal piping plan 13 for flushing the process side of the seal in crude or other process streams with particulates?
The thing to be aware of with API Plan 13 is that it does have an advantage in that you're not reintroducing process fluid continually into the seal chamber. You're actually reversing the path and taking the flow from the seal chamber back to suction. The disadvantage of Plan 13 is that from a heat removal perspective, this flow path is very tortuous. So when you're talking about high pressure and high speed applications, typically the flush demands of the seal are much higher. So you have to weigh that against the relative inefficiency of Plan 13 from that perspective. In terms of how to handle using 13 to maybe help with particulates, we have seen some crude installations in the field where they use a Plan 11 in conjunction with a 13 to kind of keep the seal chamber from not being stagnant and stuff, particulate not plating out in the seal face area. But most of the time, crude oil, you're talking about constituents that are suspended and in solution. So essentially using a Plan 13 to say we're going to maybe remove particulate in that aspect is maybe not as effective. So within certain parameters, it may be an option, but really the demands of the application have to be reviewed thoroughly before you go that route.
Well, thanks, Brian. Raul, Jim may have addressed this question during his portion of the presentation, but I think our audience would like to hear your feedback as well. Has there been any testing or experience with the diamond face technology with these types of applications?
At this time, relative to this particular product line and geared towards this market, that being crude oil, we have not yet tested diamond-coated technology or any type of diamond material. The product development team certainly took into consideration various materials, but through the testing, and it was extensive testing with over 7,000 hours of laboratory testing and torture testing and various operating parameters and speeds and sizes, it was discovered that in terms of the mechanical seal faces themselves, the standard silicon versus silicon material combination often look pristine post-test. And so what we've seen is that in terms of going through that voice of customer process with some of the historical data, and I think Jim touched on this, is that the common mode of failure tends to be that dynamic O-ring and the amount of particulate and the amount of movement in some of these machines, that was really our target. And so it was not uncommon for a seal to come out of service and the seal faces, look relatively new and look in pristine condition, yet the dynamic O-ring has significant wear, significant fretting at that balance diameter. And so at this point, we have not gone through the extensive testing of alternate materials. Once again, if you look at the matrix that was presented, those are all standard silicon versus silicon options or material combinations. And once again, over various size ranges, various speed ranges, and various operating pressures, and seal leakage has been significantly reduced in the majority of those installations.
Great, thanks, Raul. Have a question that just came in. I'm going to address it to you, Raul, and if you want to assign it to one of the other panel members, I'm sure you'll feel free to do it. When using the 8648 VRS seal, are the springs easily clogged? They are exposed to the crude oil.
Jim, would you like to comment on that question?
We have not seen the O-ring or the springs coming out of service clogged. There's enough movement of fluid through there that will allow them to stay flexible. And we don't recommend the use of a single coil spring. It just requires way too much axial space.
Good, thanks, Jim. Raul, a question for you. How have leakage rates of seals installed in the field compared with rates of the originally installed technology?
So that's interesting in that various operators go about monitoring leakage rates, whether it's based on volume or based on volume over a given time frame. I think a couple of point of references is that in instances where the dynamic O-ring would find itself fretted in, let's say, 15 to 2,000 hours of operation, and fretting to the point where a 2-gallon collection pot would fill up in, let's say, a 2 to 3 week time frame after the O-ring had been compromised. Well, in several of those installations, we're now pushing 9 to 10 to 12 months of operation where we've not yet had to go out and service the Plan 65 collection vessel. So you've seen dramatic improvements in terms of the leakage rates, in some cases even as short as 2 weeks, where constant dripping, maybe not a process stream or a cycling of that 65 collection pot and requiring service where within a couple of weeks, 2 to 4 weeks, implement the newer technology that alleviates the problems associated with that dynamic O-ring, to where you're now pushing 12 to 15 months of operation without having to pull the seal since. So it's difficult to quantify in terms of exact measurements, because every operator is monitoring their leakage differently. But in terms of time-based frequency, where we've seen 6 weeks, 8 weeks, maybe even 2 to 3 months before pulling the seal from service, the upgrade itself has led us to running, at this point, over a year's time in several instances, and continuing to operate without having been pulled to year to date.
Well, thanks, Raul. A question for you, Jim. Can different grades of durometers or elastomers be used to increase abrasion resistance?
Well, right now we're using a 90 durometer O-ring, which is a very hard O-ring, and for that reason, to resist abrasion. We do have the material, the part can be supplied in either a Viton or an Aflast material. So it does have various materials and durometers based on certain applications. But the standard offering is 90 durometer Aflast.
Thanks, Jim. Raul, another question for you. How much axial movement has been observed in the field, and how tolerant has the 8648 VRS been to higher end levels of movement?
I'd say at this point, the higher end that we've seen in terms of axial movement, and it's typically associated with a BB1 style machine, but we've seen anywhere between, I'd say as high as almost 24 thousandths of axial movement. I'd say on average, where we've applied the 8648, we've seen in the 12 to 14,000. Some operators have seen it as low as 4 to 6, but I'd say on the high end, as much as 24,000, where we were having issues with performance. The end user was having issues with excessive leakage rates, and then adopting the 8648 VRS technology, while not making that significant modifications to the machine, has translated still into much lower leakage rates. Great.
Thanks, Raul. Jim, I'll give you the opportunity to answer the final question of the webinar, and it's of a little bit more of a general nature. What has been most interesting or compelling about the development of this particular solution in the context of your overall experience and career?
Wow. This has been quite a big challenge, because it led us to what we thought was a solution of a full convolution bellows, and it led us down a path of a complete redesign of that secondary sealing element. And the ability of that secondary sealing element to resist pressure and to maintain a constant base loading has been quite impressive. And actually it was quite interesting to see the test data. And like Raul said earlier, we have over 7,000 hours of testing. So it was quite interesting to see what we thought was the solution was actually wrong and ended up down a different path.
Good. Well, thanks for that well-considered answer. And I'd like to thank the entire John Crane team with us today for their expert presentation. I'd like to thank John Crane for sponsoring today's webcast. And now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it as we use this information to improve our webinars. On behalf of CFE Media and Technology, thanks for attending, and we'll see you next time.